when we're talking about related rates, we're really beginning to apply these ideas of mathematics of change. And so anytime we're talking about a rate, we're necessarily talking, somehow it's related to slope, because slope is the rate of change of some y value relative to the rate of change of some x value. And because we're talking about slope, we're also relating things to the idea of derivative. So let's consider a couple examples. The statement John is growing at the rate of 3 inches per year in terms of calculus could be expressed as dh, the change in height, dt, to the change in time, is 3 inches per year. We could have a statement like my mutual fund is shrinking by 4 cents a day. So dm, the change in my mutual fund, dt, over the change in time, is negative $0.04, or that it would be 4 cents per day. We could be looking at the radius of a circle is increasing by 4 feet per hour. So in this case, dr, the change in the radius, dt over time, equals 4 feet per hour. Finally, we could be talking about the volume of a cone, and the volume is decreasing by 2 cubic inches a second. So dv dt, the change in volume over time, is equal to 2 cubic inches per second. So notice how the notation is related to some things, and it's directly related to this idea of derivative. Now consider a rectangle for a moment, a picture to visualize it. So we could have a rectangle, and this rectangle is 10 inches by 6 inches. So it looks something like this. These are in inches. And it happens to be the case that the sides are changing. So what we'd like to do is write formulas for both the perimeter and the area, and how fast each is changing in terms of L and W. So let's deal with the perimeter first. The perimeter of our rectangle is just twice the width plus twice the length. And if we wanted to express how the perimeter is changing, or the change in perimeter, well, we'd have to take the derivative of this with respect to time. And notice that this is directly related to implicit differentiation. Right? The derivative of p is 1 dp dt is 1 dp dt. The derivative of 2w would be 2 dw dt, plus the derivative of 2l would be 2 dl dt. Right? So the rate of change of the perimeter is related to the rate of change of the width and the rate of change of the length. Let's talk about the area of this same rectangle. So we know the area of this rectangle would be length times width. And if we wanted to have a way of expressing how the area is changing, well, again, we would take the derivative. And the derivative of A would be 1 dA dt, because we're taking the derivative with respect to time. And we'd have to use the product rule to take the derivative of L and W. So again, the product rule, the derivative of the first, so in terms of L, this would be dL dt, times the second, so W, plus the first times the derivative of the second, which would be 1 dW dt. Now that we have these formulas, we might be able to do something once we know their rates. So let's consider this rectangle again. But now we're going to be told that the length and width are increasing at the rate of 2 inches per second. And what that means is that dl dt is 2 because it's increasing by 2 inches per second. And we're told that dw dt is also 2 inches per second. So now if we revisit the question, what is the change of the perimeter? Well, we have that formula. We know that dp dt equals 2 times dw dt plus 2 dl dt. So, since both dw dt and dl dt are 2, then dp dt, the rate of change of the perimeter, would be 8 inches per second in this case. Let's consider the rate of change of the area of this same rectangle. When we're told that dA dt is related to dL dt times whatever the width happens to be, plus the length times whatever dW dt has to be. In our case, this thing is 6 inches wide and 10 inches long, so dA dt would be equal to 2, the rate of change of the length, times the width, which is 6, plus a length of 10 times 2, the rate of change of the width, which means the area is changing by 32 square inches per second. So that's how fast the area is changing if the length and the width are changing by 2, increasing by 2 every second. A thing that's important to notice about this 32 inches squared per second is this is the rate of change of the area when the side lengths are 6 and 10. And if the side lengths were different, the rate of change of the area would also be different. Right? So it's only the rate at that specific instant. Let's consider option D for the same example, where we're told some different things. Right, so we're told about the length is decreasing, so dl dt is decreasing, so it's negative 2 inches per second. But dw dt is increasing at half an inch per second. So how does that affect the perimeter? Well, the rate of change of the perimeter now, if we substitute different values into the same formula, would be 2 times 1/2 plus 2 times negative 2. Or we find that the perimeter is changing by 1 plus negative 4, or the perimeter is decreasing by negative 3 inches per second. With regard to the area, again using what we already know about dA dt, we're told that dL dt is negative 2, and our width happens to be 6, plus our length is 10, and dW dt is 1/2. So this is negative 12 plus 5, or negative 7 square inches per second. This would be an example of related rates. And we'll just continue to do more examples in other parts.